Hi, welcome to the Bitstream Computing Hackathon being held here at University of Wisconsin. This is a hackathon that was put together by some students in my research group here, in the farm group, and we're looking forward to having you participate and learn a little bit about what Bitstream Computing is and how it can be used to deploy very efficient neural network implementations that are suitable for use in edge or IoT devices. This hackathon is really motivated by the emergence of edge devices or Internet of Things devices that have sensors attached to them and that monitor the real world. And the goal of many of these devices is to provide either some end user with useful information or perhaps even take actions autonomously on their own. And what we really want to try to learn about in this hackathon is how these IoT devices sense and interpret the world, and how we can build them in a way that minimizes power use and maximizes battery life, and how we can train and program them and design them to meet these kinds of goals. One example of this kind of device would be this Ring doorbell here, which fundamentally, you'd like for it to be able to tell you, is someone at the door, someone standing there or not. And my understanding is that currently these devices don't really do that processing on board natively. They ship it up to the cloud, and algorithms run up in cloud servers, and then the answer comes back from there. But of course, ideally, for privacy reasons and many other reasons, it would be ideal if you could actually perform that processing locally on this tiny device. But there are many challenges associated with making that a realistic goal. So the scope of our investigation in this hackathon really is what are known as edge or IoT devices. These are devices that, again, have some kind of sensor typically attached to them, maybe more than one, and they're responsible for monitoring what's going on in the real world. And we have to build them in such a way that the cost is reduced as much as possible, so they're inexpensive and can be deployed, all over the place. Oftentimes, we're very concerned about power and energy efficiency, particularly if the devices are battery operated. And of course, we care a lot about accuracy and functionality for these devices as well. And the challenge is that, especially for sensory processing, the most powerful algorithms that we utilize these days are based on neural networks. And neural networks, if sort of deployed naively, are very power hungry. They can require millions, even billions of multiply accumulate operations to be performed per image, per inference, which is prohibitive for a lot of these power constrained or cost constrained devices. These neural networks also can have a very large memory footprint, and in general are going to be a poor fit algorithmically for fitting into these systems with these constraints. Before digging deeper into how we engineer these designs, let's just do a quick recap on what a neural network is. So a neural network is an algorithmic structure that is intended to mimic neurons in the brain. And really, you can think of a neural network as something that approximates a function. So given some input x, which can be multidimensional, we want to apply a function to it that computes some output based on the values of those inputs. And oftentimes, when we deploy neural networks for a particular task, it's because we don't understand that function very well. We don't know what that function looks like, and instead we approximate it with a neural network. And so neural networks are very useful and very powerful in this regard because you can essentially train them to recognize or to implement functions without really having any insight or understanding of what those functions really even look like. And what you see illustrated here is kind of a toy example of a neural network. On the left-hand side, we have 3 green neurons that are the input neurons. On the right-hand side, we have 3 yellow neurons that are the output neurons. And in the middle, we have the 5 red neurons, which form what's known as the hidden layer. And the basic idea here is that each of the neurons in the system, in this case, because it's a pretty simple single-layer neural network, really just the red and the yellow neurons learn to respond in different ways to different values on their inputs. And so all of the red neurons are connected upstream to the 3 green neurons. All of the yellow neurons are connected upstream to the 5 red neurons. And each of the neurons computes its response using this equation shown at the top here, where you essentially compute the dot product of a set of weights and the corresponding inputs to that neuron and sum them all up. And so you multiply weights times activations, sum them all up, and then typically you'll pass them through some activation function, which provides some additional functionality. Basically, it makes this entire system convert from being a fully linear system to a nonlinear system, which allows it to then capture functions that are not just restricted to being linear in nature, but also nonlinear. So this kind of an architecture now allows you to, again, approximate any given function where that output is a function of its inputs. And the way this neural network learns what these weights are, so when we start with a brand new network, these weights are unknown. Typically, we'll initialize them to some random values, and then we'll start exercising the network, and we'll learn what those weights need to be using an algorithm called gradient descent. And gradient descent, simplistically, is just the following. You present some input, let's say it's a picture that you found on the internet to this neural network. It evaluates, so each of the neurons computes this dot product, runs it through an activation function, and passes it on to the downstream neurons until you get to the output. Now you look at this output and you compare it to the known value. So you can only do training like this with labeled data sets where you know what the output is going to be. So you present a picture, you know because some human labeled it that that's a picture of a dog, let's say, and so the output vector that comes out should correspond to the representation that you want for a dog. Let's say the top yellow neuron means dog, the middle one means cat, and the bottom one means turtle. So you'll set a value of 1 for the top neuron and 0 for the other two as that label. And then you will compute the actual response of the network, and then you'll look at the error in that output. And that error essentially then guides you in how you change all of these weight values in order to push them in a direction or to descend the gradient in the downward direction so that you reduce that error or reduce that loss term. So you'll basically examine every W sub I value in every neuron and say, if I move this up or if I move it down, will that reduce the error? And whichever direction reduces the error, I'll move a little bit in that direction. And then I'll repeat the process with thousands of images of dogs and cats and turtles. And over time, all of those weights will converge to an approximation that will then produce the right response on the output when you present the network with a picture of one of those three things. So that's simplistically what a neural network is. Hopefully that's enough background for you to kind of understand the rest of this presentation and the purpose of the hackathon. Now, an important extension to the concept of neural networks was proposed back in the 1980s by Yann LeCun. And the idea behind this approach is to apply concepts from image convolution to the design of these neural networks. You may remember what convolution is from your earlier signal processing courses. You may not, but the basic idea behind convolution is to apply sort of a pattern match to a set of neighboring pixels. So it might be a 3x3 set of neighbors or a 5x5 set of pixels, like is shown in this example network, and essentially convolve those pixels with a pre-existing pattern, and the response will then determine how close of a match that input is to that sort of initial template. And you can use this to do things like edge detection and so on in a programmatic way. Now, the cool thing about applying the notion of convolution to neural networks is that we don't actually know ahead of time what patterns we should be looking for. So in the lowest level of the network, we're typically looking for simple features like straight lines of some orientation, but we don't know exactly what we're looking for. When we integrate this concept into a neural network where we're training the network, we actually are defining what that set of features is on the fly based on the examples that we're learning from. And so the idea here is, again, you present images, you apply these convolutions to them, you push them all the way through to the output, and then you compute the error, and then you tweak all the parameters to say, okay, what values should these parameters hold in order to give me a reduced error, meaning something that's closer to the right answer. And again, you iterate on this training process, and eventually you get to the point where all of these convolution operations now are collecting, are basically characterizing the input in this kind of new convolutional namespace that has been learned over time. And I guess that the tricky thing, we'll talk a little bit more about 3D convolution in a few minutes, but the tricky thing here is that we think of convolution as a 2D thing where you're just looking at pixels in X and Y dimensions, but really there's always a third dimension. So even on the input side, if you're looking at color input, you typically have 3 channels, red, green, and blue, giving the intensity of the pixels in each of those colors. And so the inputs are multidimensional, three-dimensional, but all of the intermediate layers in these convolutional neural networks are multidimensional as well. So you're basically scanning across the image, performing this 5 by 5 or 3 by 3, whatever kernel size you're using, convolution on all these pixels. And then in the next layer, you're generating not just one output saying, oh, okay, this is the likelihood that there's a horizontal line at this location, but you're performing a bunch of them. One convolution for the horizontal, one for the vertical, one for the diagonal, and so on. Whatever the features are that layer is trying to detect. And again, we don't know what they are because the convolutional neural network is being trained to figure out what those are. So again, we can apply this, and then as we go through subsequent layers in the network, we apply what's called a non-unit stride. So we sort of, instead of moving over pixel by pixel, we go every 2 pixels for a stride 2 case, and that basically now increases the receptive field. So the size of the original pixels in the image that are being now considered by this particular convolution is now 4 times as many. So if you go from a 5 by 5 convolution in the first layer, and then you do a stride by 2 in the next layer, now you're looking at 4 of these 5 by 5 chunks. So you're really looking at a 10 by 10 chunk or 100 pixels, again, times 3 channels at that level. So you sort of progressively apply these non-unit strides to get to a narrower, smaller and smaller set of convolutions. And then eventually you feed the outputs of those convolutions to a fully connected layer of hidden units that's used to sort of represent that information then to the output layer, which you then train to classify now the image, in this particular case, into one of 10 classes, because this network was designed to detect handwritten digits, of 0, 1, 2, 3, up to 9. So that's essentially the concept of a convolutional neural network, and that's a powerful concept and one that has become extremely popular in the machine learning literature in the last 10 years. In ways, CNNs derive their inspiration from the mammalian visual cortex, which is hypothesized to sort of do a very similar iterative process of looking, in the retina, looking at essentially pixels, in the LGN, looking at contrasts, and then the upper layers of the visual cortex, V1, V2, V4, sort of extracting progressively higher level features until you finally get to the inferotemporal temporal cortex, where you actually have neurons that are firing in response to particular objects with labels like cars and buses and motorcycles. So there's a lot of evidence that the mammalian visual cortex operates like this, and convolutional neural networks are taking inspiration from that concept. So CNNs have been around for a long time. There's been an explosion of interest in them in the last decade or so, and this graph just kind of shows how crazy people went. So as you go from left to right on this graph, you're sort of increasing the number of operations that you need to perform. So remember, again, for a dot product, the number of inputs determines how many multiplications you have to do and how many additions you have to do, because you have to multiply every input with its corresponding weight and then accumulate them all to compute the dot product. And so the sort of larger your layers are, the more layers you have, etc., the more operations you need to do to actually evaluate the whole network from the input to the output. And this just shows a bunch of example networks that have been proposed over the last decade or so, and how they've grown as you go from left to right in terms of the number of operations required, and also the size of the dot that you look at here is the number of parameters. So the total number of weights that model requires in order to operate. And you can kind of see that some of these got to be very, very expensive in terms of operations. 40 gigaops means 40 billion operations. 40 billion multiply accumulates have to be performed to evaluate this network for one image. In the last 5+ years, there's been a lot of effort now to try to make a concerted effort to reduce the cost without compromising the accuracy. And so you can kind of see that if you look at the green arrow here. The mobile net architectures, which is what we're focusing on here in this hackathon, have essentially matched the performance in terms of the y-axis, the total accuracy of these very large networks, but at a fraction of the cost. And so there's a lot of clever engineering that goes into achieving that goal, and we'll talk a little bit about that here. So given this growth in the size of neural networks that are very accurately solving particular problems, There's been a concerted effort in the research community to try to reduce the cost of these deep neural networks. And I want to point to one particular project, the TinyML project at Harvard, which has been focusing specifically on trying to reduce the cost of these so that they can be deployed on these very energy constrained, cost constrained IoT platforms. And this hackathon also is sort of focused into this same space. And so we're going to look at three aspects here in the remainder of this presentation. One is, what are some of the things that people have done to redesign these networks to reduce cost, and we'll specifically look at the mobile net architecture from Google. We'll look at something called quantization, where you essentially try to map these variables or parameters in the network that are represented as floating point values, typically using 8 bytes or 4 bytes, to much smaller integer values, which are cheaper to operate on. So that's a process called quantization, where you essentially map these values into this much more efficient representation, but at the loss of some precision. And that reduces the data path complexity, simplifies the data path, and also reduces the memory footprint. And then the third thing we'll look at, and really this is the primary focus of the hackathon, is how we do what's called pruning. So a lot of the connections or synapses in these neural networks are sort of ineffectual. They're not providing much value, and so there are ways that people have come up with for removing these ineffectual connections, pruning them out of the network to again shrink the size of the network in terms of the number of parameters and the amount of compute required. All right, so how do we redesign these networks? Well, I'd refer you to the MobileNet v1 paper from Google, which is referenced here. It's on arXiv. It's a great paper. It's a fun read. If you're looking for something to spend an hour on, I recommend it. But the basic idea here in this network was to work hard to optimize the number and the type of each of the layers in the network. So let's not have 57 layers. Let's not have 99 layers. Let's see if we can get by with a smaller number of layers. Let's see if we can sort of tailor the operation of each of these layers to perform the job that we need them to perform, but not with such extravagant cost. And one of the parameters they provide is something called a scaling factor. So the idea here is that you can just provide a scaling factor and it will scale the number of channels in each layer accordingly. And we're actually going to use a 25% or 0.25x scaling factor for this hackathon because that seems to be good enough for the task that we're working on. And then the final thing, which I'll say a few more words about, is they replaced sort of the conventional convolution, three-dimensional convolution operation with something called a depth-wise separable convolution, which performs nearly as well as 3D convolution, full 3D convolution, but is much, much, much cheaper to train and much, much, much cheaper to actually exercise, to do what's called inference. So let's dig into that a little bit. What do we mean by 3D convolution? So 3D convolution, again, if you're familiar with convolution, then convolution, we essentially define some size region around the current pixel of interest. In this example here, it's a 3x3 convolution. So we're going to look at the 9 surrounding pixels corresponding to the ij location, or the xy location in the current image that I'm interested in. And I'm going to assign weights to each of those 9 locations and then compute a result. Now, I say 9 locations. It's not really 9 locations because even at the input layer, you typically have 3 channels. You have red, green, and blue RGB pixel intensities. And so you have 3 channels that's shown in red, green, and blue here. And then you're looking at the 9 pixels in the neighborhood. So you're looking at a total of 27 pixel values. And so you have 27 parameters that you're going to now multiply against the corresponding input values to compute the response to this pixel, to this one location. And then you're going to repeat that process, at every XY location in that layer to generate all the outputs for that layer and then feed it to the next one. And you're also going to repeat it for every channel output because you also now typically will have you might have 3 channels of R, G, and B intensity coming in, but you might want 16 or 64 or some larger number of channels on the output to be able to represent all the different features that ultimately you're interested in, right? I mean, simplistically, you might think of it as you want 1 channel for vertical lines, 1 for horizontal lines, one for lines that are at 45 degrees, ones that are at 135 degrees, and so on. And so you want channels for each of these features each of these feature types that you're expecting to see. And of course, you don't know what those features are until after you've trained the network, and so you want to put in a bunch of room for a bunch of features, and then as the network trains, it figures out how many of these features it actually needs. So anyway, so the cost of performing 3D convolution has to do with how large is the convolution. 3 by 3 is the typical convolution. So that's the number of that's the sort of size of the convolution. The cost of the whole layer is of course determined based on the X and Y dimensions. So if it's a large image, a megapixel image, X and Y are going to be very large. If it's a smaller image from a lower resolution camera, X and Y will be smaller. But then also the number of input channels, CI. So again, the camera will typically give you 3 channels, but in these intermediate layers in the network, you'll want at least 16, all the way up to 1024 channels. And so you have some channels on the input side, you have some channels on the output side, and then the total number of each of those is what ultimately determines the total number of weights and the total number of multiply accumulates that you need to execute in order to evaluate that layer. And then to do the whole network, of course, you have to add up all those for all the layers. So there's just some examples here that show for different dimensions of input, 96 by 96 pixels or 228 by 228 pixels, and different numbers of input and output channels, how many total weights are you going to need in that layer? So that ranges from 4,600 for a small one to 37,000 for a medium-sized one to 4.7 million parameters for a large one, and then the number of multiply accumulate operations that you need to apply to evaluate that layer now, ranges from 42 million to a couple billion to 245 billion. So, at the extreme range of that, you're kind of getting to the point where trying to map this onto some low performance microcontroller that you might find inside your Ring doorbell is probably not feasible. It's not going to be able to do this in real time. Even the 1.9 billion is probably excessively slow. So the cost of evaluating the neural network, which is called inference, is very, very high. But it's also very expensive to train because the more parameters you have, the sort of longer it takes for them all to settle to their right values during training. And so having a network with fewer parameters means it'll train more quickly, which is an advantage at design time. Okay, so in the MobileNet architecture, they replaced this 3D convolution with something called depthwise separable convolution. And pictorially, you can kind of see how that differs here if you look at the colored representation. So in a depthwise separable convolution, what you're going to do is you're going to channel-wise do the spatial convolution first. So in this case, I'm going to look at the neighboring 3 by 3 pixels in the blue channel and compute now a response to that blue channel. And then I'm going to look at the green channel separately and then the red channel separately. So I'll basically generate kind of a summary representation of that neighborhood, of that 3 by 3 convolution neighborhood in the blue, the red, and the green first. And that's a much cheaper operation because I just need to look at 9 pixels for each of those. Now I still have to repeat that for every X and Y location in my input field, in my input image, but it's still much, much cheaper because I don't have to look across the channels. And so now I have kind of a summary representation of each of the channels for that location, and then I apply what's known as a 1-by-1 convolution, where I just look at essentially those 3 channels now at that location and compute an output for that. So that's what's shown here is the red, the green, and the blue are now combined in that 4th equation to generate an output. And then again, you're going to have multiple output channels here, so you're going to repeat that last computation multiple times. But the net effect is that you're going to require a number of parameters that is substantially smaller because the convolutions are smaller. You don't have to look in the depthwise dimension. Even though you're doing these 2 separate steps of convolution, it's computationally much cheaper and requires a lot less memory. And you can kind of see if you compare this table to the one on the previous slide, you're getting at about a 10x reduction in the number of weights and the number of multiply accumulates. And so that leads to much cheaper evaluation or inference and much faster and cheaper training as well. So this is kind of the really big deal in MobileNet that made a big difference in terms of the cost of the neural network itself. Okay, so the second major technique that we want to talk about for reducing the cost of neural networks is quantization. So if we look at historically what happened with microprocessors, we went from 8-bit to 16-bit to 32-bit, and most recently to 64-bit microprocessors, starting in the 70s and then ending up in the last decade or so, because wider was generally considered better. You could do better precision and a larger range for larger, address spaces. These are all good things for computing. But this came at a cost, and what's been realized, lately is that we can actually save quite a bit of memory space and simplify the data paths needed to compute on these operands if we represent the values, in particular in these neural networks, with much smaller data types. And so Van Hook showed back in 2011 that for a lot of neural networks that were popular at the time, both the weights and all of the activations flowing through the network could be represented with just 8 bits, and still we could still deliver reasonably good accuracy out of these networks. So we really didn't need all that precision, and we just had to find a way to correctly map these values into that space and do a little bit of fine-tuning to make sure that the network still performed well. So this whole process was driven, really by this drive for efficient neural network inference. So the natural question that comes to mind when you think about this is, how narrow can we go? What is the narrowest value that we can actually still usefully operate on in a digital system that's 1 bit? So if 1 bit is, the least amount of information that we can convey in a digital system, we can build hardware that's very, very simple. As we'll see, we can build hardware that costs almost nothing and that can perform arithmetic operations on these 1-bit values. But of course, 1 bit doesn't give you much range or much precision. But it turns out that you can stream a bunch of bits through and convey much greater precision over time. So you can sort of flexibly stream a longer stream of bits to get more precision, or stream a short stream of bits if you don't need much precision, depending again on your application context and how much error you're willing to tolerate. And this sort of approach to building this computational data path hardware has its origins in 3 related areas: rate coding in biological spiking networks, pulse density modulation in audio applications, which is a way of representing digitally the sound signal, and then stochastic computing. So we'll touch on each of these briefly. So rate coding in neurons, this graph just kind of illustrates measurements that people make of neural activity, where on the x-axis is time, on the y-axis is a neuron, and then a spike or a mark here indicates that a neuron has fired, and you can sort of draw conclusions about the activity of these neurons by looking at how often they're firing in some given time window. So that's what rate coding is. So there's strong belief that your brain will encode information in the rate that the neurons are firing at to represent the intensity of a response to something. So this is sort of a biological angle on where this idea is coming from. Stochastic computing is an approach to building data paths that was originally proposed by von Neumann, but was really sort of brought to fruition and realized in digital form by Gaines in the late 1960s. And this work was primarily driven by a desire to build fault-tolerant systems where even if some bits failed or flipped or were incorrectly computed, over time, as long as you pushed enough bits through, you would still get the right answer on average. And this is accomplished by assigning a uniform weight to each bit. So in a typical binary system, we have low order bits with low weights and higher bits with high weights. And if you flip one of the higher bits, you get a lot of error. In a stochastic circuit, any bit has the same value, has the same weighting. And so if you flip 1 bit, you're not introducing a whole lot of error. And the advantage of computing in this stochastic form is that arithmetic functions are usually trivial to implement. So the canonical example is this AND gate shown here, which is processing a stream of bits in time from right to left, and then producing a result, which actually now numerically, if you interpret these streams of bits as expectations of the value being represented, shown in parentheses here, again, half the bits of the value S1 are set, so that's 4 out of 8 or 0.5. 6 out of 8 of the bits of S2 are set, so that's 0.75. If you multiply those two values together, you'd expect to get 0.375 or 3/8. But the answer we actually get, because of the way the ones and zeros line up when they run through the AND gate, is 2/8. So it's not quite right, but it's very close. And the theory is that the more bits you push through, the closer you eventually get to the right answer, as long as you're properly randomizing the input streams so they're not correlated with each other. So why should we use bit streams for computing? Well, the fundamental advantage they have is that they provide very low-cost data paths that operate on a very flexible representation. Flexible meaning we can extend the length of the bit stream if we want more accuracy, or we can push a very short bit stream through if we can tolerate a lot of error in our output. And also, bit streams fit naturally with existing sensors and actuators in embedded systems. Like audio data is often represented using PDM, which is very similar to bit streams, and other sensing modalities are also very, very close to this and can easily be converted to and from bit streams. Conversely, why should we not use bit streams? Well, it is a very inefficient representation. It's linear versus logarithmic in terms of its capacity. So in a conventional binary number, if you add 1 bit to the length of the binary number, you double the range of values that you can represent. In a bit stream, to get basically double the range or double the precision, you have to double the number of bits. And so it's linear in terms of its growth, which is not efficient. Similarly, it's inefficient in time because long bit streams take a long time to compute. And there are many algorithmic issues. Not all the operators that we need are available or known, so sometimes you have to kind of invent new implementations for operators. Pipelining computations can be challenging because sometimes you need to accumulate a bunch of bits before you can pass a known value through some transformation. Many analytical tools that engineers use to design algorithms and circuits, like Z-domain analysis, don't really work. And because of the limited range and the small amount of precision that you have available to you, you have to apply scaling factors to your inputs and to all your parameters in your designs. And this is not a trivial process. And there are many practical issues. There are really no software tools, no programming languages, no existing compilers, or there were none of these things until we started working on this problem in my research group a few years back. Because we have spent a lot of time in our group building some of these tools. And they're open sourced on GitHub. You can find them easily. Currently, the current version of the development chain is based on a language called Julia. That's what we'll be using in this hackathon as well. And these tools support a broad variety of bitstream constructs. We have a bunch of sample example benchmarks and so on that are implemented, and they support development, validation in an emulated bitstream mode, and also automatic synthesis of a bitstream data path by spitting out Verilog. So lots of neat functionality there. We're not going to touch much of it in this hackathon, but you can certainly go play around with that if you're curious. All right, so let's hop back to the kinds of circuits that we need to implement neural networks. Fundamentally, the building block that we need is a dot product engine. And in this case, now we want to build that dot product engine in a way that it operates on bit streams. As you can see on the figure on this slide, there's basically 3 different components that are needed to build this dot product engine. On the left-hand side, you see something called a stochastic number generator. This is basically a linear feedback shift register in LFSR, not an expensive circuit, but you do need one of these for every weight or every parameter in your neural network because you need to generate essentially a bit stream that encodes the value of that parameter so that it can be operated on in the data path. Then in the data path itself, you need basically AND gates, one for every synapse or for every multiplication in the numeric baseline implementation. So those are cheap. 2-input AND gates are inexpensive. And then we need a bit count circuit labeled as add here to basically count up the number of ones that arise from all of those 1-bit partial products that are being generated by those AND gates. And then this circuit basically needs to be replicated, within each layer of your network for every channel and for every XY location. And so there's a lot of instances of these dot product engines, but each one of them is relatively inexpensive, and so we can afford to replicate lots of them to build our entire network. Now, the key thing here, again, is that in terms of cost, the length of the bit stream that you feed through this design will approximately determine its accuracy. And so longer bit streams will take longer to evaluate, but they will give you a more precise answer, and vice versa. So this is a trade-off that you'll explore in this hackathon, looking at different lengths of bit streams to see, sort of where's the sweet spot for length of bit stream versus accuracy. Another challenge that we face when we're trying to implement neural networks on bitstream substrates is that the range of values that we can represent with a bitstream is limited to -1 to +1. So we're stuck using activation functions that adhere to this rule, and many popular activation functions like ReLU can easily exceed this range. It turns out that the traditional tanh function, or hyperbolic tangent, is a good fit because it takes input from an arbitrary range and transforms it into the shape shown on the top left here, that is limited to now values between -1 and +1. And so we can accurately represent those values in a bitstream environment. However, the cost of implementing a nonlinear function like tanh is quite high. We either have to use some complex arithmetic to approximate it, or we have to use a lookup table. However, there's another substitute activation function that we can use that works quite well called hard tanh, or a piecewise linear tanh. Shown on the top right here, you can see the plot of that illustrates that essentially in the active range it's a linear function, and then outside the active range it just saturates at +1 and -1. So this is a function that is trivial to implement in bitstreams because essentially we're already limited to this range. So we don't even have to apply any hardware to mapping the x value on the x-axis to the corresponding f of x value on the y-axis. It just kind of works automatically out of the box. So this is a great fit. If you look on the website, in the tutorial section, there's a little bit more text there about the specific flavor of hard tanh that we're using. But this is essentially what we're going to use in this hackathon. Just as we have to limit the activations to the allowable range of -1 to +1, which is all that bitstreams can represent, we also have to limit the weights that are used as parameters in each of the layers to this range as well. Otherwise, we won't be able to perform proper multiplication with those weights. So to achieve this goal, we basically add a loss function term to the loss function for the overall network that penalizes weights that fall outside of this range. And that loss function is basically using the soft shrink function plotted here up on the top left, which applies no penalty as long as a weight value is in the allowable range of -1 to +1. But as soon as it falls outside of that range, it applies a linear penalty. And when we apply this additional term to the loss function during training, we find that the weights converge very quickly into the allowable -1 +1 range. So this works really well, except for one additional problem. During training, we insert what are called batch norm layers between the convolutional layers in the network, and this is a technique that's basically normalizing the outputs of those layers around their mean and standard deviation of 0, a mean of 0 and a standard deviation of 1. And this is a technique that's used during training to target what's known as the vanishing gradient problem. And so if you're training a network that's deep and has lots of layers, the gradient that is back propagated from the output back to the input layers, towards the input layers, tends to become very small as it crosses layers, and the batch norm layers essentially beef it back up so that it doesn't vanish, and so that we can actually properly train layers that are closer to the input and further from the output. Now the issue here is that when we actually take this trained neural network and start using it for inference, the standard procedure there is to fold out this batch norm layer into the convolutional layers by essentially taking the values that it's, the multiplication and shifting that it's applying to the output of that layer, and folding it into the bias and the weights of the preceding convolutional layer. This transformation again, works really well, except that as a result, even if we've trained our convolutional layers, weights and biases to fall within the acceptable range, after this folding of the batch norm layer, they can now once again exceed that range and not work properly. And so what we do to resolve that issue is that we first fold the batch norm layers into the convolutional layers, and then we fine-tune for a few more epochs using this same loss function that I just described, and we find that the weights indeed quickly converge back to the allowable -1+1 range when they do that, and the resulting neural network now works very well for inference. It matches the accuracy of the network before we did the batch norm layer folding. Now, one thing to keep in mind here is that if you're going to do extensive fine-tuning or extensive training, which you would typically do after, say, a round of pruning, which we'll talk about next, you probably will need to put these batch norm layers back in. So you need to reinsert them. We have code for that in the distribution for the hackathon so that you can put the batch norm layers back so that you don't run into the vanishing gradient problem again when you're trying to fine-tune your pruned network. So yes, just keep that in mind. If you take the batch norm layers out in order to evaluate the performance of your network, and then decide to continue pruning and continue the training process with more fine-tuning, you'll probably need to reinsert the batch norm layers. Otherwise, the fine-tuning will not work. It will start diverging because of the vanishing gradient problem. You know, oftentimes, if you start with some neural network like this toy example that we looked at the beginning of this presentation, it turns out that a lot of the connections, which are the blue edges here between the layers and the neurons, and even sometimes some of the neurons themselves are not necessary. And this is not a new observation. Again, LeCun and others back in the 1980s, proposed approaches for doing this kind of pruning. So pruning means eliminate edges and possibly eliminate neurons that are not effectual, that are ineffectual, that aren't doing much good, aren't having much impact on the output. And we can identify them by looking at the weight value, the absolute value of the weight on the synapse. If it's a low weight, then if it's nearly zero, then multiplying by a value that's nearly zero is going to give you an output that's nearly zero, which will by definition have very little impact on the output of the dot product. So perhaps we can just strip it out. And so you can kind of do this iteratively and start removing the low weight synapses, and then you'll see that the corresponding dot product operations are going to have fewer inputs, so they're going to have to do less work, and they're going to have to store fewer parameters. So it'll be cheaper. And then sometimes you'll eliminate a bunch of these edges, and you'll find that a particular neuron, in this case the second red neuron from the top, becomes completely disconnected. When it's disconnected, there's no reason to compute that neuron itself, so you might as well just completely eliminate that neuron itself, as well as all the synapses leading up to it. And so you kind of do this iteratively. When you prune things, you also want to fine-tune the network, so you want to do some more training iterations. So again, you want to present an input and a known output, compute the error, and then adjust all of the weights in the network accordingly so that they'll sort of compensate for the fact that this synapse and or neuron is now missing. It isn't contributing, so some of the other neurons are going to have to, or other synapses are going to have to contribute to make up for the fact that that neuron or that synapse was stripped out. And as you do this, then that will have an impact on the hardware, because every time you eliminate a synapse, you're going to eliminate the stochastic number generator that's providing that weight value, and also the AND gate, and also the fan in to the adder. So there'll be a ripple through effect from eliminating that single synapse or weight. And then if you prune an entire channel, well, that means you're eliminating an entire dot product. And so there's a big savings there. You don't need the adder unit. You don't need any other circuitry that goes into it. Now, the two types of pruning that we'll be looking at in this hackathon are unstructured pruning, where you just kind of target synapses, and structured pruning, where you just only target channels. And you'll have to play around with those two modes, and see what kind of results you get, and decide what strategy you ultimately want to pursue. This slide illustrates the overall flow for the hackathon. We're going to provide you with a pre-trained version of the MobileNet network, pre-trained for this particular task. And we encourage you to basically start with that pre-trained MobileNet and focus on pruning approaches to improve on it. However, if you wish to train that network from scratch, you can certainly do that. The code is all there, and the training and validation data is all there as well. Be aware of the fact that this will take you a while. So even on a decent GPU, like I have a GTX 1080 GPU on my PC, it'll take about 1.5 hours. So you may not want to do that. But if you have access to a GPU, you can certainly do that as well. For the rest of the steps of the hackathon, a decently fast CPU will suffice. You don't really even need to have access to a GPU. Of course, if you do have a GPU, Julia will run quite a bit faster on that as well. All right, so starting with the pre-trained mobile net, the first thing you'll want to do is decide on a pruning strategy. Do you want to prune synapses? Do you want to prune entire channels? How much do you want to prune? Once you've applied the pruning changes, invoke the pruning code in the Julia code base, then you'll want to fine-tune your model using, again, the training data to make sure you recover the lost performance that will basically happen as soon as you do any pruning. Your accuracy will drop, but you should be able to fine-tune it to recover most of that loss. Once you're happy with your result, and you may want to iterate on that, you may want to prune multiple times, gradually prune 10% per pass through this iteration loop. Eventually, you'll end up with a design that you're happy with whatever degree of pruning you're happy with. At that point, you'll want to go ahead and remove the batch norm layers, and then fine-tune with the network that doesn't have the batch norm layers. And this basically allows you to now recapture the accuracy, or basically push the weights, parameter values, or the weights in your network into the allowable range of +1 to -1. Once you're done with that fine-tuning, this is typically just a couple of epochs, then you can invoke the evaluation script, which will apply the test data now, and will quantize everything in your network so that it's suitable to run on the Bitstream substrate. And we'll evaluate the performance of that network. And if you're happy with that, you can go ahead and submit that through our website. If you're unhappy, you can go back and iterate that basically any step along the way. Evaluation for this is going to be determined with a set of test images. Because testing is fairly expensive, we're going to use a very small test set, just 100 images. These are excluded from the training or validation sets. They're only in the test set. And we'll use a script to estimate accuracy under this bitstream mode. And the accuracy will drop from the level of pruning that you're doing, and it will also drop from the quantization effects. And so if you choose a bitstream length of 100,000, your accuracy will probably be unchanged from the training accuracy. But if you choose a bitstream length of 1,000, you'll definitely get much lower accuracy. So you'll have to pick a bitstream length that gives you that right trade-off between the execution time, which is proportional to the length of the bitstream, and the accuracy that you're getting. And it may be the case that you'll find a network that is heavily pruned will need a longer bitstream, and vice versa. If you don't prune as aggressively, you might be able to get by with a shorter bitstream. So there's kind of a trade-off there between these two operations that you'll have to explore that space and see where you get the best result. The cost of the design is going to be the relative silicon area. Again, what is the cost of all those AND gates and adders and random numbers, stochastic number generators after you pruned, and we provide a script to do this for you. And then energy is measured per inference. So how much does it cost? How many joules will you consume if you execute this on the hardware that you've designed now after pruning it? So we also provide a script for estimating this. Just caveat here. These are all estimates, right? We're not actually, designing the real hardware that's going to be too time-consuming of a process at this point for this hackathon. So these are just, high-level models that are estimating all of these effects. In terms of hackathon logistics, we do have a help session to help you get started. That'll be run at the time and place shown on the slide or shown on the website. In terms of the evaluation metrics for the hackathon competition itself, we'll be asking you to report your accuracy on the test set as reported by the evaluation script, the area cost after pruning, the energy cost based on your pruning and bitstream length that you set, and we have a couple of compound metrics as well that will look at accuracy divided by area and accuracy divided by energy. And on both of these compound metrics, of course, higher is going to be better. Once you're happy with your submission, you can write up a report and report your model and your results via the web form. We are asking that you submit a brief write-up of what you did to describe, the choices that you made, the decisions that you made, the pruning and fine-tuning flows, what choice you made for bitstream length, any design trade-offs, any further parameters that you changed or tweaked, and then again the resulting area energy estimates from the tools and the accuracy for the test set, and any lessons learned and conclusions, and really any other feedback that you want to provide to us since we are hoping to offer this hackathon multiple times on future dates. And we also want to get a pointer to your final BSON model file so that we can actually load it in and test it ourselves to make sure that everything matches what you recorded. Before wrapping up, I just want to acknowledge some of the folks who've contributed to creating this hackathon and running it. So first of all, Nitya is my current student who has put a lot of work into the quantization and bit streamlining portions, implementing the new activation function that works well within a Bitstream environment, and updating all of the scripts and tutorials. So I really appreciate her help on this. In a previous iteration of this hackathon, Kyle Darawala and Ravi Raju, two of my former PhD students who were students at the time, put together the scripts and the data sets and so on before that. So I really appreciate the efforts that they put in 2022. But overall, many students over the years in my research lab have contributed to the research that has brought us to this point, and that work has also been funded by the Air Force Research Lab as well as the National Science Foundation, and additional prior students have worked on this as well, including Rohit and Michael. And finally, the TinyML project at Harvard, which has created the benchmark that we're using, has been instrumental in enabling this hackathon. In conclusion, I just want to welcome all of you to come and learn all about leading edge Wisconsin research into ultra low power neural networks. If you do join the hackathon and participate, you'll learn a new programming language, Julia, which is probably new to you. You'll learn about how to compute with bit streams. You'll learn how to train a powerful neural network called MobileNet. You'll learn how to make it efficient by pruning it, tuning, and quantizing it. And finally, if you submit your results, you are in line potentially to win some valuable prizes. Just a reminder that we are kicking off the hackathon at the time and place shown on the slide here, and the website is already live. So go ahead and get started with tutorials and getting set up for the hackathon today. Welcome.